So last week we had a Blackboard lunch talk from the topology program for all the rest of us, and today we're very lucky to have Jean François Joanny from Collège de France and the Curie Institute in Paris, and he's going to be representing the films program and telling us about membranes and interfaces. So thank you, Jean François, and I'll pass the room to you.
Okay, so good morning or good evening for me. The other session is called Physics of Elastic Films, from Biological Membrane to Extreme Mechanics. And what I want to do is give you examples of this physics of elastic films that I will take from biological systems, essentially cells and tissues. Now, I don't pretend to be general. I will just give you examples which are bias my own interest and my own research. If I kind of mess up the technology, please excuse me. This is the first time that I give a talk like this on my iPad in front of Zoom, so I hope it will work well. What I want to start with is kind of very classical things, is what I will call the statistical physics of membranes. Now, the statistical physics of membrane was started by a German physicist, German theoretical physicist called Wolfgang Helfrich. And what Helfrich was studying is molecules which are called phospholipids, which are the molecules that form the cell membrane. They self-assemble, and they make this type of bilayers that I sketch here. So you see one layer of molecules in contact with water on top, and one layer of molecules in contact with water on the bottom. Now, if you look at it at the kind of mesoscopic scale, the thickness of these bilayers is extremely thin. It's between 2 and 3 nanometers. And you want to look at it at the scale of hundreds of nanometers. So essentially what these molecules make is an infinitely thin surface which is fluctuating in space, in water. So what Helfrich did is a statistical physics of fluctuating surfaces. He did it in two cases. When the surface is a plane, fluctuating plane, so fluctuating sheets. And the second case that he studied is when it wraps around the sphere and is called a vesicle. Now, to do the statistical physics, you need a Hamiltonian. And what Helfrich did is that he inspired himself from the mechanics of membranes. And in the mechanics of membrane, you expand the energy that will play the role of a Hamiltonian in powers of the curvature. So the energy, the Hamiltonian, which is called the Helfrich Hamiltonian, is the sum over the surface of an expansion in powers of the curvature. So the zeroth order term is the membrane tension that I will call gamma. I will assume here that the membrane is symmetric, so there is no linear term, and the second term is proportional to the square of the total curvature of the surface, and there is a bending modulus that I will call K here. In the original Helfrich energy, there is a third term, which is proportional to the Gaussian curvature of the surface, but this term can be integrated into a constant that only depends on the topology. So for everything I will say it's a constant, and I won't talk about it. Now there are two parameters in this Hamiltonian, the surface tension and the bending modulus. The bending modulus is an energy, so you can define a length scale that I will call D, which is square root of the bending modulus divided by the tension, and I will put a 2 here that you will see later. What I want to do is show you what happens with a vesicle. So I will show you a vesicle. So here is a vesicle. The size is something like 50 microns, so it's much thicker than the thickness of my membrane film. There is water inside, water outside, and it's held here by a glass micropipette. The experiment that I want to show you is pulling by a point-like force on the vesicle. So you have here a bead, which is a few microns radius. And what's done is people hold the vesicle with a pipette and pull on the bead with an optical tweezer. And you will see what happens. No, you don't see what happens. You see what happens here. You pull on the bead, and in between the bead and the vesicle, there is a formation of a very thin tube that goes from the bead to the vesicle. So by exerting this force, what I'm doing is I'm pulling a tube. It turned out that the tube has a constant radius. Now I let you do the calculation. You just put the tube geometry into this energy, and you minimize with respect to the radius, and you get this radius d that I was talking about, which is square root of the bending modulus divided by twice the tension. Let me give you orders of magnitude. This tube is like 30 nanometers. That's a good order of magnitude. The bending modulus I will express in terms of the thermal excitation. So it's K in units of KT. And for the cell membrane, it's something like 20 KT. And the surface tension, which is the other parameter, is a small surface tension. Gamma is 10 to the minus 3 Newton per meter. Physicists got very much interested in this question of fluctuating membrane. And the reason that they got interested in that is that fluctuations are big for this fluctuating membrane. So let me discuss what I will call giant fluctuation. So for a minute, I will take the limit where the surface tension goes to 0. So gamma is very small. So the only term in the energy is the bending modulus. It's like a free sheet, a free paper sheet that you would look and which is fluctuating because of thermal fluctuations. So what I will do is I will take a piece of membrane of size L. And I want to estimate this Hamiltonian for the piece of membrane of size L. Before I do that, I have to be slightly more precise, and I will define what people call the Monge gauge. So I will, again, this time I go a surface which is fluctuating in space, and I will measure the undulation of this membrane on top of a plane here. So I will define a plane, and I will measure at each point in the plane the height of the membrane that I will call U of R, where R is a two-dimensional coordinate in this plane. Now you can re-express this Hamiltonian as a function of U, and I will only do it if the slope is small. Now in this case, the curvature is just a Laplacian of U, and the surface element is just dx dy times 1 plus 1/2 of gradient U squared. Now if I plug that into this energy, I get H equals sum dx dy, and then I have two terms, the term that comes from here, which is gamma over 2 gradient U squared plus K gradient squared U squared. Now if I neglect the surface tension, if I calculate orders of magnitude, if U is the order of magnitude of the amplitude, the curvature is of order U over L squared, and the energy H is of order K, so there's a 2 here, so it's L squared for the area, and U over L squared squared, so it's K U squared over L squared. Now, this is a Gaussian Hamiltonian, so what statistical physics tells you is using the equipartition of energy, this Hamiltonian for a size L should be of order KT. So the fluctuation is such that U squared average This is of order KT, if I take the average. So it's KT L squared divided by K. What this tells you is that there is no new length scale in this problem. The only length is the size of the membrane, and the amplitude of the fluctuation scales with the size of the system. So this is a problem with giant fluctuations, and you can use all the fancy theoretical techniques that people use for critical phenomena, for instance. If you want to be more precise, you can calculate the amplitude for a mode Q, and I will write the amplitude of the fluctuation for a mode Q. This amplitude, U, Fourier transform of U for a mode Q, squared modulus, is KT per mode, so it's the area times KT, divided by the gamma term gives gamma Q squared, and the bending terms gives K Q4. So this gives you for each wavelength or each wave vector the thermal amplitude of these modes. One of the things that you might be interested in is the equation of state of these monolayers. Now, the important thing that one should realize is that the monolayer, the membrane has a size A, but the projected membrane on the plane has a size A naught. A is fixed. A is the number of molecules that I put in the membrane, but A0 varies, and if I add tension and I pull on the membrane, A0 will change. The more I pull, the more the tension gets larger, the larger the area A naught. So the equation of state will amount to calculate A minus A naught, how much of the area goes into the fluctuation. This is simply sum of dr of 1/2 of gradient U squared. Now, if you use this mode decomposition, you can calculate it explicitly. And it tells you that A minus A naught is proportional to A. Then there's KT over 8 pi times K. And then there's a logarithm of Q max squared times kappa over gamma. Now, Q max is the shortest distance cutoff. In practice, it's the thickness, 1 over the thickness of the membrane. If I increase gamma, A minus A naught decreases and A naught increases. So if gamma increases, A naught increases. And if I decrease gamma, A naught decreases. So I can stretch the membrane by increasing the tension. And the tension is just due to the folding of the membrane with itself. And when I pull on it, I kind of unfold these fluctuations. Now, there are many, many experiments on these ideal membranes. In particular, Carlos Marquez, who is one of the organizers of this session, is currently doing lots of experiments. And these experiments are extremely well described by these very naive models that I'm kind of describing here. Now, of course, these membranes are ideal, and the cell membrane is more complex than that. So what I want to do now is take you from this ideal problem of statistical physics to a more realistic cell membrane. So this will be my second part. Now I will show you some kind of sketch of a real cell membrane. So I go back to my figures, and the cell membrane can be sketched like this. So you see in red the lipid molecules, but you see that there are lots of other molecules that are inserted in these membranes, and these molecules are proteins. Now the mass of protein in the membrane can be extremely high. In the membranes of the mitochondria, 70% of the mass is proteins and 30% is lipids. So there is more, in this membrane, there are more proteins as lipids, and the picture that I gave you is certainly not correct. this kind of idealization of the membrane with lots of protein floating around was proposed by two biologists, Nicholson and Singer, and it's called the Mosaic fluid model, which is how people describe membrane in the biological literature. Now, what I want to do is try to show you some examples of what proteins do in membranes and what should I add to this ideal picture that I showed you before. So there are essentially four types of effects that I want to discuss. The first one, and I'll be very fast with that, is that the lipids are not homogeneous. It's a mixture of lipids. And these lipids phase separate, so there are two-dimensional phase separation between liquids. What it means in practice is that you have region where you have more than one lipid and region where you have more of other of these phospholipids. One of the things that you might have heard of is what are called rafts, which are small, a few nanometers or tens of nanometers, regions which are phase separated from the rest of the membrane. They include lipids. Most of the time, they include also proteins, and it's clearly a non-equilibrium phase separation. So I won't talk about that. What I want to tell you about is the protein which are inserted in membranes, and I will discuss three types of protein. The first one is passive proteins. And what I call passive proteins is proteins that don't consume energy, so they don't get energy from the hydrolysis of ATP. Then I discuss filaments interacting with the membrane. And the filaments that I will discuss are called actin. And the third thing that I want to discuss is what I will call active proteins. These are proteins that consume ATP, which means that hydrolyze ATP into ADP, and then consume this chemical energy to exert a function. If there are active proteins in a membrane, it means that there is a flux of energy onto the membrane and that the membrane is not at thermodynamic equilibrium. So my statistical physics description is certainly not true for these passive membranes. So let me start for these active membranes. So let me start with passive proteins. And I will give you an extremely simple example of passive protein, which are proteins that sense curvature. So I will consider a membrane which is curved. So it can be curved in this direction, or be curved in this direction. And I will assume that the protein is polar and it likes to bind in this configuration. So of course, it can bind on both sides in the membrane. So if the membrane is curved downwards like this, it binds from the top. If the membrane is curved upward, it binds from the bottom. I can, for this problem, write what I will call a membrane Hamiltonian, or a membrane energy. And this membrane energy will depend on the geometry of the membrane, on the curvature, but it will also depend on the concentration in 2 dimensions of the protein that go downwards, phi minus, and the protein that go upwards, phi upwards. So the membrane energy is a sum over the surface of the membrane. There is a term which is a curvature term, Kc squared. Then there's a mixing free energy between these two types of proteins, so the one that point out and the one that point down. So plus F of phi up, phi down, which includes the surface tension. And then there is a coupling between the concentration and curvature. Because the proteins are polar, the term linear in curvature is allowed, and of course it should be opposite for the two types of protein. So I will have something like plus some coefficient times the curvature times phi plus, phi up minus phi down. This term respects the symmetry. If I change C in minus C, I replace phi up minus phi down. And that's my only criterion to choose it. Now I will change variable. I will call psi phi up minus phi down, and phi the total concentration. I can rewrite this Hamiltonian. It's sum ds k over 2 c squared plus f, which will be a function of phi and psi, plus chi times psi. Now what I can do is minimize this energy with respect to curvature. If I minimize with respect to curvature, I will obtain the curvature. I will minimize, and there's C here. I will minimize these two terms, and I will get a curvature which is such that C is minus chi psi over K. Then I can plug that back into the energy, and I get H equals sum over the area, ds. I will write the sum of these two terms, which I insist is negative. It's minus chi squared over 2k psi squared plus f of psi and phi. Now this term here gets minimized if psi gets large. So what these terms do is that it will create a finite value of phi. If chi is too small, there will be no effect. And if chi goes above a critical value, there is a phase transition where chi is finite. But psi finite means that phi plus is different from phi minus. So there is a phase separation in the membrane with regions with downward curvature. So we have regions of upward curvature and regions of downward curvature. In the region of downward curvature, the proteins will be like this. In the regions of upward curvature, the protein is like this. So this is a phase separation which has to be because of the geometry at finite wavelengths. And if you want to calculate the wavelengths, you have to perform a much more fancy theory than the one I'm presenting here. But what I want you to keep in mind is that because of geometrical effect, proteins can phase separate in membrane and associate proteins of the same type. There are experiments currently on that. There are proteins which are called bar proteins, which are proteins that sense curvature, and people like Patricia Bassereau in Curie are studying in detail how these bar proteins associate and make domains inside the membrane. So that's passive proteins. The second type of protein that I want to study is actin, and acting at the membrane form what's called the cortical layer. So cortical.
Jean François, we have one question.
Yes.
Buddha, do you want to ask your question?
Yeah, that's fine. Jean François, thank you very much, and nice to see you. So a question which I had was, the way I'm thinking about this is the variable psi. In StatMech language is probably playing the role of a magnetization-like variable. And I was wondering whether a grad psi squared term should also be present in the Hamiltonian to the lowest order of Q? Is it 2 squared?
So that's what I'm saying, that there's a psi squared term, but there are also grad psi squared terms. And these grad pi terms are the ones that fix the period of the oscillation that I draw here, which I didn't go into.
Oh, okay. Thank you very much. Thank you. Sorry.
That's what I call the more detailed theory of that. So I want to show you a cortical actin layer. So this is an electron microscopy image of this actin layer. In blue on the left, you see the phospholipid membrane. And in red, you see these actin filaments. These actin filaments are more or less parallel to the membrane, and they form a layer which is something like, I don't know, 200 nanometers, 500 nanometers, something like this. And they form some kind of a gel. So when the membrane deforms, it has to deform the actin gel which is below. Now, what I will do is I'll talk about them in 2 steps. And the first step, I just want to show you another type of experiments, which are vesicles, so the same one that I showed you earlier, plus actin. Now in the cell, the actin is inside the cell, below the membrane, in the image that I showed you. The experiment that was done by Cécile Sykes at Institut Curie, she took a membrane, she put actin filaments on top of the membrane, and she looked at the deformation of the vesicle because of that. So it's easier to show you a real experiment. So the actin is in green and the membrane is in purple here. So you see the vesicle, you see the actin layer around the vesicle, and you see on the left that the vesicle buckle. So if the actin layer is thin, the vesicle buckles, and it buckles like a ping pong ball which you have kind of deflated, or that you squash a ping pong ball. So they can control this deflation, and they control it using usually osmotic pressure if they want to do it quantitatively. Now you can compare that to what happens if the actin layer is thick. So you see that on this side, the actin layer is much thicker. And you see that the shape that the vesicle reaches when you deflate it is extremely different. You don't have this strong buckling with a wavelength which is more or less the size of the vesicle. Here you have an undulation at a finite period around the vesicle. So that's kind of easy to explain. So there are 2 states, what I will call the buckled state. For thin actin layer, and what we call the wrinkle state for thick actin layers. So how can you see that? Actin forms a gel, so it's an elastic material. It's a soft elastic material with an elastic modulus, something like 1000 Pascal. If it makes a very thin layer, you can say that the membrane is made by the real membrane plus this actin layer, and there's a bending modulus which has 2 contributions. And if you take a surface which only has a bending energy, it buckles like a ping pong ball. So this is the buckle state. If the actin layer is very thick, the membrane buckles, but the deformation doesn't penetrate all the way through the actin layer. So it's like buckling the membrane in an elastic medium. And it's well known that if you buckle something in an elastic medium, the instability doesn't occur at 0 wave vector, it occurs at finite wave vector. So this is the same kind of instability. When the layer is thin, it occurs at 0 wave vector. or at the very vector, which is the size of the object. When the size is, the thickness of the actin layer is large, the instability occurs at finite wave vector. And this is what we call wrinkling. I won't be more quantitative here. I'll come back to that at the end, and I'll show you what the wavelength is in this case. However, this is a vesicle, and this is not the cell. Now, if I go back to my image of the actin layer, you see that there are the actin filaments here, but you see these green points here. These green points are molecular motors. These molecular motors are what biologists call ATPases, which means they consume ATP, and they consume ATP and they produce force. In a very naive way of thinking, you could see the motors as grabbing two filaments and pulling on the two filaments. So when I insert molecular motors like this in actin, they tend to contract the actin layers. So let me try to be a little bit more quantitative about that. So let me make a sketch. So the membrane I will draw here. So this is the lipid membrane. The actin filaments are inside the cell. So they are inclined like this. Now, if I want to be more precise, they grow and shrink. They grow from the surface, and they depolymerize all over the layer. So there's a finite length of this filament, and they are more or less parallel. And then there are molecular motors. And the molecular motors cross-link this actin filament and tend to contract the network. Now, this is typically what I would call an active system, and you could study that using all these theories which have been made in the recent years on active matter. I won't do that. I will be much more naive. What you learn from active matter is that if there is an orientation, and here the filaments are oriented more or less parallel to the membrane, there is either a contraction or an extension in this direction. We know experimentally that there is a contraction by the motors of the actin filament. So what this means is that because of the molecular motors, the filaments are contracted like this, parallel to the plane, and so there is a stress. There is a stress which has this orientation. That corresponds to a contractile stress. If I cut the stress, the filaments shrink on themselves. So there is a parallel stress here, which is positive. Now the surface tension is just the integral of the stress in the layer over the thickness of the layer. So the actin tension gamma actin is just this stress sigma parallel times the thickness h of the layer. Which means that now if I consider this as the layer which is bounding the cell, the total cell tension that I call gamma C has two contributions. There is one contribution from the membrane, and there is one contribution from actin. Now, I told you that the contribution from the membrane was something like 1 millinewton per meter, or 10 to the minus 3 newton per meter. The contribution of the actin is much larger than that. It's something like 100 times larger than that. So the tension of the cell is not dominated by the membrane. The tension of the cell is dominated by actin. Now I want to show you an experiment which measures directly the tension of the cell, and this will kind of show you how it works. It's a very similar experiment to the one I showed you in the beginning. So this is a cell now, and the cell is grabbed by a micropipette, and you swallow, put a low pressure at the end of the micropipette. So the cell is pulled by a pressure difference into the micropipette. Of course, if the cell has a tension, there is a Laplace pressure here, and the difference in pressure between outside and inside is given by this Laplace pressure. Now, if you increase the pressure and you decrease the pressure inside, the radius of curvature will increase until it becomes the radius of curvature of a micropipette. And then at this point, the cell is swallowed, and the difference in pressure is given by the Laplace pressure, which is one times the cell tension divided by the radius. So just like this very simple device, you can measure the tension of the cell, which is due to the actin molecular motors pulling on this actin filament and putting them under tension. So that's the tension of the cell. Now I want to show you an application of this cell tension, which is related to cell division. When a cell divides, there is this process called mitosis, where it separates its chromosomes. So the chromosomes of the two daughter cells are well separated. This is called mitosis. But in the end, the cell has to cut into two daughter cells. This is called cytokinesis. So what I want to show you is how cytokinesis is controlled by this actin cortical layer that I just showed you. So I will do that with pictures again. So this is a big egg. It's a sea urchin egg. Just before cytokinesis, it's spherical. It's spherical because this cell has a tension, and the tension forces a minimal area for a given volume. The minimal area is a sphere. And then you see that it starts to separate into two, and the way it does it is there is a region here where it's pinched, and it takes this peanut shape, and then there is a ring, which is a ring of actin, that pinches the cell in the middle, and you see the ring decreasing, 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 and at the end, the cell separates into two parts. So we studied that by looking at the properties of this cell actin, cortical actin. So the cortical actin layer is in blue here, and at the beginning it's homogeneous. Now it's known in biology that what happened is that at the equator of the cell, at the early stage of cytokinesis, the actin density is increased. So there is more actin here, there is more molecular motors at this point as well, so the tension is larger. So you increase the tension in a small region at the equator of the cell. Now the tension integrated over the small region is like a line tension. So what you want to do, you have a circle where this tension is larger, and what you want to do to minimize the energy is to shrink the cell. So the cell is shrinking at this point, and it's pinched little by little, and in the end you get a configuration like this, where the ring is almost collapsed to zero, and you can more or less compare quantitatively the shape of the cell to the shape of the sea urchin here, and you find the same shape. Now this is, however, not the end of the story. The tension is large here, but the tension hasn't changed here. So what it means is that there is a gradient of tension at the surface of the cell. The membrane is liquid, so if there's a gradient of tension, it's like a gradient of pressure in two dimensions. It induces flow. So actin should flow from the poles to the equator. This is called the cortical flow because of this gradient of tension. I will show you a slightly more sophisticated picture. which is this movie here. We increased at the middle the density of motors. It pinches the cell, and the calculation is done in Lagrangian coordinates. And you see these points which are converging. This is the flow of actin from the pole to the equator. So you see this point are moving from the pole to the equator. There is a strong line tension here. The dissipation is the dissipation of this flow of actin. The actin is viscoelastic, and this is what fixes the time scale of this cytokinesis. Now, of course, in the end, you have a very small ring, and this ring must break. It cannot be described by synchronous mechanics because this is highly regulated. What I mean by that is that in kind of popular language, before splitting into two, the cell checks that everything is correct on each side. And this you cannot reach with only physics or mechanical arguments. So this is what happens for this cortical layer. The third type of proteins that I want to talk about is active proteins. So active proteins for me are proteins that consume energy. And proteins consume energy in the form of ATP. It's coupled to a chemical reaction, and ATP molecules are hydrolyzed. There are many types of active proteins. One of them that I just talked about is molecular motors. Another type of active proteins is what are called pumps. Pumps are molecules that actively take ions and move them from one side of the cell to the other side. So it's an active process by which you take ions on one side and you push them on the other side. There are other types of active proteins like GTPases, which are proteins that don't consume ATP but consume GTP, which is kind of the same thing as ATP, but with a guanine base. The ones that I want to discuss very briefly are these pumps proteins. So let me again sketch a membrane. And the membrane has pumps. The pumps, of course, have a direction. They can pump ions either from inside to outside. And if I do it on a vesicle, they will go randomly into the membrane. So there will be pumps that transport ions from inside to outside, and there will be pumps that transport ions from outside to inside. Now, when the pump transports an ion, it creates locally a small flow of water, and that creates a force in the fluid. Now, if the membrane creates a force in the fluid creates a force on the membrane. So the activity of these pumps creates a distribution of forces along the membrane. So I have to be more precise. If you look at the mechanics more correctly, a pump cannot be a force, it has to be a force dipole. So it's a distribution of force dipoles. Which means that in addition to the thermal fluctuation, the membrane has kicks, which has these force dipoles, and these force dipoles increase the fluctuation of the membrane. So the activity of pumps increase membrane fluctuations. And what you can do with that is calculate the amplitude of the membrane fluctuations due to both thermal fluctuations and these random force dipoles that act on the membrane. So the square of the amplitude in Fourier mode is what we had with a passive membrane, so KT over gamma Q squared plus K Q4, except that both the tension gamma and the bending modulus kappa are renormalized, and they take lower value. So gamma tilde is smaller than the original gamma, and K tilde is smaller than the original K. And the change in tension in modulus is related to moments of this force dipole that I was talking about. And then there is another correction, which is 1 plus some constant times Q squared over kappa tilde Q squared plus gamma tilde. So this is the prediction that you can make for an active membrane which is covered with pumps. These can be compared to experiments, and this was done in the group of Patricia Bassereau at Institut Curie. And this type of formula, first of all, the membrane fluctuations are increased when you measure them. And second of all, this formula describes well the fluctuations that you measure. Now, a more naive and simple way to characterize fluctuations is to try to define an effective temperature. And the way you do it is you measure what I call the equation of state. So remember, this was a measure of the area minus the projected area as a function of the tension on the membrane. So what you want to do is measure that, and instead of using the temperature, you fit it with an adjustable temperature. Now, if you do that, which is certainly not extremely well justified theoretically, what you find is that the effective temperature for this protein that was studied, which is called bacteriorhodopsin, is about twice the room temperature. So these pumps not only are active, but they are extremely active because they multiply more or less what plays the role of temperature by 2. Now, I want to come back on that now and show you maybe a last example, and I want to talk about red blood cells. Now, red blood cells are cells which are much simpler than the other cells because they have no machinery to divide and replicate. They are extremely simple cells. Also, when you look at red blood cells and you shine them with light, you see the fluctuation of the red blood cells. And these fluctuations are what are called the flickering of the red blood cell. Now, the red blood cells have a membrane, and below the membrane, they also have a cortical layer. And this cortical layer is much simpler. It's made of polymers which are called spectrin. That form a triangular lattice. So the spectrin are flexible polymers, and they are arranged like this. And for many purposes, you can assume that these polymers are spring. So you have the membrane, And below the membrane, you have this lattice of spring, which is bound to the membrane at the junction points. So at this point here, it's bound to the membrane. However, the binding is not permanent. It binds, unbind, binds, unbind. So there is a kinetic of binding, and this kinetic of binding is active, which means these proteins here, which are called ankyrin or PK4, they consume energy. Now, the question that we had with a colleague called Timo Betts is whether a red blood cell was an equilibrium system or a non-equilibrium system. To me, this is kind of a stupid question, but there were papers that were claiming that you could use the equilibrium theory to describe red blood cells. In a sense, the philosophy is that anything which is alive should be out of equilibrium. And to me, red blood cells are alive, so they should be out of equilibrium. Still, people were claiming that they were equilibrium systems. So what this guy, Timo Betts, started to do is try to see whether he could measure the fluctuation, check the fluctuation dissipation theorem for a red blood cell. So a red blood cell has this funny shape, which is something like this, called stomatocytes. And what Timo did is that he took a small bead and he attached here on the surface of the red blood cell. And then he measures two things. He measures the fluctuations of the position of the bead, so fluctuations of the bead. And what he measures is a power spectrum. Let me call that C of omega at a given frequency. And he also measures the response function. Chi of omega. Now, for a system at equilibrium, these two quantities are related, and they are related by the fluctuation dissipation theorem. Which tells you that C tilde of omega is KT, 2KT over omega times the imaginary part of chi. So you measure chi, you measure the imaginary part, and then what you want to check is that this quantity C goes like 2KT times chi double prime. So let me show you the result of the experiment. So this is this is a discrepancy between theory and experiments. I use omega and he uses the real frequency, so this is where the pi's are coming from. This curve here, lower curve, is the imaginary part of the response function. And this upper part here is the spectrum of the fluctuation multiplied by what it should be multiplied to satisfy the fluctuation dissipation theorem. You see that at high frequency, the two curves superimposed, so the fluctuation dissipation theorem is satisfied. Now, if you believe, like I do, that this non-equilibrium character comes from the binding and unbinding of the spectrin network to the membrane, there's a time scale for that. If you go faster than this time scale, you don't see the non-equilibrium effect, and the system should be at equilibrium. Still, if you go at low frequencies, you have enhanced fluctuations. In an equilibrium system, the fluctuations should be like chi double prime, and they are enhanced. So there are active fluctuations again, as in the previous case, and this active fluctuation tells you that the system is out of equilibrium. And there is no effective temperature in this case because the effective temperature would depend on frequency, and that doesn't have much sense. There's another thing that goes with it, is you can prepare your red blood cell, do the experiment, and then wait. So you wait 16 hours, 24 hours, 48 hours, and the red blood cell ages in the solution that he prepares them with. If the red blood cell ages, it dies, and when it dies, it's a perfectly equilibrium system, and you should satisfy the fluctuation dissipation theorem. And indeed, if you wait, you see that this point is decreasing and the two curves superimposed, and you get an equilibrium system. So yes, the red blood cells are alive, and they don't satisfy the fluctuation dissipation theorem. Then what we did, and I won't take you into that, is we made a model for the binding and unbinding of the cortical network to the membrane, and coupling it to the chemical reaction of binding. And we coupled that with the mechanics, and we were able to explain these two curves that disagree. So active phenomena for these cells are important, and the cells are clearly non-equilibrium systems. I think I'm kind of done with my time, no? I don't hear you, Mark.
Sorry, yes, this is a good point to...
This is a good point to stop, I think. I had other things in conclusion that I wanted to show you other examples, but let me stop here. For instance, there are other ways to put membranes out of equilibrium with fluxes of lipids going to the membranes. Let me skip that and stop here, and thank you for your attention.
Thank you very much, Jean François. That was great. Do we have some more questions? Leo, you can ask it.
Oh, I was just, Jean François, I just wanted to find out is, do you expect the ratio of the C and chi double prime to saturate at low frequencies, or is it divergent, or?
So the ratio of chi and chi double prime, of C and chi double prime is just the ratio between these two curves. So at high frequency, I mean, it's renormalized by the frequency.
Right.
I mean, this is what should, at equilibrium, the square point, which is the upper curve, is multiplied by frequency and divided by KT in such a way that it should be equal to chi double prime at equilibrium. So
right,
the
but
ratio
I'm
between these two. So
for the non-equilibrium theory, what do you expect that ratio to go to at low frequencies?
Or it should go like a constant multiplied by F or divided by the frequency. This is what the fluctuation, I mean, as this goes to a constant, this is what it tells you.
No, sorry, that's the FDT, that's the for fluctuation, that's for equilibrium systems.
No. Yes, what's written here is for equilibrium systems. But if you look at the experiment, what it tells you is that the fluctuations times the frequency divided by KT is a number times chi double prime.
Right, so I was wondering how that number behaves as a function of frequency at low frequencies.
Or at low frequency in a complicated way. But
does it go to, but it has a,
it has a finite value at zero frequency.
Has a finite value. Okay, that's all I want.
I mean, it goes like this curve here, it goes up like this curve.
Okay, that's what I want to know, what it does at low frequency. Yeah, okay, thank you. Very nice talk. Thank you so much.
Other questions? Leo.
Yeah, can you elaborate a little bit more about the dipole for the active pumps? Why they can only generate dipoles and not actual forces that move the membrane?
These are systems where there is no inertia. So if you take any object, the total force on this object should be zero, particularly on the pumps.
I see, no inertia, okay.
Yeah, and inertia is really negligible.
Okay.
in the, I don't know,
Okay,
it's
thank
orders
you.
of magnitude smaller than what we get as flows.
Okay, thank you.
Okay, I think unless there are other questions, please thank Jean François. You probably can't hear the applause, but there is. And I just want to thank everybody for coming from both programs and locals, and have a good rest of the day or evening.